Welcome to the step-by-step solution to the IB Mathematics Higher Level Analysis and Approaches Paper 1, Time Zone 1, May 2021 exam paper. We hope this video will help you prepare for your mock or final exams for IB. Please note this video is primarily focused on problem solving, so concepts will not be taught in this video, but rather shown how to use the concepts that you would have learned in the IB syllabus to tackle some of the IB exam questions. If you wish to get further clarification on some of the mathematical concepts taught in IB, please fill in the form below and we can arrange a personalized tutor to offer you help in your IB journey. Feel free to pause at any moment during this video if there is anything unclear in the solutions, as you may need to rewatch the solutions several times to fully grasp how to tackle the question properly. Before we begin, please leave a like on this video and leave a comment telling us how you found this video and any feedback for future videos we upload. Don't forget to subscribe to this channel for more content like this. Let us begin. Okay, so for question 1, we have the following question. The graph y equals f of x for minus 4 less than or equal to x less than or equal to 6 is shown in the following diagram. For part A, we have to find the value of f of 2 and f of 2 based on the provided graph. To determine the value of f of 2, we realize that 2 refers to the x value of this graph, so we need to identify the x-coordinate where x is 2. If we look at the graph, the solution is going to lie somewhere on this line, since this is where x equals 2. Now, we just need to find the point where the graph meets this x equals 2 and find its associated y value. So if we go up and up, we eventually stumble upon the line where x equals 2, and if we try and find the associated y value, we find out that it is 6. Therefore, the answer to A, I, is f of 2 is equal to 6. Now, for determining f of 2, we need to use the information from A, I. Remember, another way to represent the function provided in this question is writing it as f of 2. So all we need to do is substitute the value of f of 2 into f of x again, and find out its associated y value. From A, I, we know f of 2 is 6, so when we plug it into this function, we end up with f of 6. The final step is just finding out what the associated y value is with this new function. So looking at the graph, we find out that when x equals 6, y equals minus 2. Therefore, the answer to A, 2, is f of 2 is equal to minus 2. For part B, we have a transformation question involving scaling and translation. The easiest way to solve this question would be to draw out a table and compute the new values of the transformed graph and plot them on the graph. So, looking at this table, we have the original graph values from the provided domain, and now we just need to apply the transformation to calculate the new values. Let's do it with x equals to minus 4. So we know when x equals to minus 4, y equals to 4 for f of x, and so to determine g of x, we substitute f of x equals 4, meaning the calculation will be 1/2 multiplied by 4, which is 2, and then we add 1, which means we end up with 3. Let's do it again with x equals to minus 2. When x equals to minus 2, f of x equals 4, so we do the same thing again, and end up with 3 again. Simply repeat this for the other values mentioned on the graph, and we end up with the following table. Lastly, all we need to do is plot these points on the graph and connect them, and we would have come up with a solution to part B. Let's move on to question 2. This question is about sequences and series. Consider an arithmetic sequence where U8 is equal to S8, which is equal to 8. Find the value of the first term, U1, and the value of the common difference, D. Okay, so to solve this question, we have to make use of the following formula which is provided in your formula booklet. As there are two different variables we have to determine, we will need to make use of simultaneous equations to solve this question. So let's set up the two equations based on the information we know. Using the first formula mentioned in the formula booklet, we can set up an equation with u1 and d as variables, since we know the 8th term in this sequence is equal to 8. So, we have u8 is equal to u1 plus 7d, resulting in our first equation to be u1 plus 7d equals to 8. Now, we can make use of the second formula mentioned in the formula booklet, as we know that the sum of the first 8 terms of this sequence is also equal to 8. So we can do S8 is equal to 8 divided by 2, brackets 2 multiplied by u1, and then add 7d, and close the brackets. After some basic simplification, we end up with our second equation, 8u1 plus 28d equals to 8. Since there isn't an exact common term between equations 1 and 2, we have to transform one of the equations such that there is a like term in both equations that can be eliminated. So there are infinite number of ways to do this, but the easiest option would probably be to multiply the first equation by 4, and then subtract that equation from the second one. Multiplying the first equation by 4 gets us 4u1 plus 28d equals to 32, and by subtracting this with the second equation, we are able to eliminate the variable d, such that we can solve for u1 first. We end up with minus 4u1 equals to 24, and we can divide both sides by minus 4 to determine the value of u1, which ends up being minus 6. Great, we have found out what the first term of this sequence is. Now, to find the common difference, all we need to do is substitute u1 back into either of our two equations we initially set up, and solve for d. Let's use the first equation for demonstration purposes. We have u1 plus 7d equals to 8, and if we substitute u1 for minus 6, we have minus 6 plus 7d equals to 8. We can add 6 to both sides, leaving us with 7d equals to 14, and finally dividing both sides by 7 allows us to find that the value of d is 2. You can try doing the same with the second equation and you should end up getting the same value as well. Therefore, the answer to this question is u1 is equal to minus 6 and d is equal to 2. Question 3 is about using box and whisker plots to determine some values in the plot. A research student weighed lizard eggs in grams and recorded the results. The following box and whisker diagram shows a summary of the results where L and U are the lower and upper quartiles respectively. We know that the interquartile range is 20 and there are no outliers in the data. We have to find out the minimum values of U and L, which based on the diagram provided, are the upper quartile, also known as Q3, and lower quartile, also known as Q1, values respectively. If you have studied anything about box and whisker plots, you would know that the following formulae can be used to determine whether a particular dataset contains outliers or not. As this dataset does not contain any, and we are asked to find the minimum value of U and L, we can still make use of these formulae by setting the outlier value to the maximum value in the dataset, which according to the diagram is 75. So we have 75 equals to Q3, which is U, plus 1.5 times the interquartile range, which is provided in the question as 20. 20 multiplied by 1.5 is 30, and solving for U gets us U equals to 45. Therefore, the minimum value of U is 45. To determine the value of L, since the question specifies the word hence, we are expected to use our answer in Part A to solve Part B. So, we can make use of the interquartile range formula, which is Q3 minus Q1. As Q3 is U and Q1 is L, we have U minus L equals to 20. We know U is 45, so we can solve for L and find out that the minimum value of L should be 25. Therefore, the answers to this question is that the minimum value of U is 45 and the minimum value of L is 25. Moving on to question 4, we have a differentiation question. We have two functions, f of x which is equal to minus brackets x minus h close brackets squared plus 2 multiplied by k, and g of x which is equal to e to the power of x minus 2 plus k, where h and k are real numbers. The first part of this question, we are asked to find the first derivative of f of x. Now, based on the type of equation this is, we can make use of the chain rule, which is provided in your formula booklet to solve this question. We can set a variable u equal to x minus h, and then differentiate f of x using this u dummy variable. This means our new equation is f of u is equal to minus u squared plus 2k. The first derivative of u squared is 2u, and the first derivative of 2k is 0 since we are differentiating with respect to u and there is no u variable in 2k. Now remember we haven't incorporated chain rule yet, as we need to differentiate the u variable we set also by multiplying it to whatever we have so far. So the first derivative of our u dummy variable is in this case 1, as the first derivative of x is 1, and h is a constant so its first derivative is 0. This means we end up with the final answer of the first derivative of f of x being minus 2 multiplied by x minus h. We have to show that h equals to e plus 6 divided by 2. To do this, we make note of the information that there is a common tangent between the two functions at x equals to 3. This means we can use the first derivatives of both functions and set them equal to each other when x equals to 3, and from there we should be able to determine that h indeed does equal to what the question has specified. We set u to be x minus 2, and do the first derivative of e to the power of u plus k. The first derivative of e to the power of u remains e to the power of u, and k is gone as it is a constant. The first derivative of our u dummy variable is 1, as remember the first derivative of x is 1, and since minus 2 is a constant, its first derivative is 0. As such, we have the first derivative of g of x to be e to the power of x minus 2. Now, we can substitute x equals to 3 into both functions, and solve for h. We have minus 2 multiplied by 3 minus h is equal to e. Expanding the brackets yields minus 6 times 2h equals to h, and through some basic moving around, we get h equals to e plus 6 divided by 2. Awesome! Lastly, we have to determine the value of k using our previous answers. Now that we know what the value of h is, we can use the original functions to solve for k, as there is a common tangent at x equals to 3, which implies there is an intersection between the two functions at x equals to 3. So, we can set f of 3 equal to g of 3, and solving through this should yield the exact value of k. We have minus 3 minus h squared plus 2k equals to e plus k. We can expand the brackets first and subtract k from both sides, which leaves us with minus 9 plus 6h minus h squared plus k equals to e. Keeping k on its own and moving everything else to the other side yields k equals to e plus h squared minus 6h plus 9. Notice how we can factorize h squared minus 6h plus 9 into h minus 3 squared. Substituting h for e plus 6 divided by 2 into this, we can simplify the terms inside the brackets and end up with k equaling e plus e divided by 2 squared. Expanding this brackets results in k equaling e plus e squared divided by 4, which matches what the question wanted us to prove. Question 5 is all about trigonometric identities. For part A, we have to show that sine 2x plus cosine 2x minus 1 equals to 2 sine x brackets cosine x minus sine x. To do this, we can make use of the double angle identities that are provided in your formula booklet, namely the identities that sine 2x equals to 2 sine x cosine x and cosine 2x equals to 1 minus 2 sine squared x. Replacing sine 2x and cosine 2x for these values results in 2 sine x cosine x plus 1 minus 2 sine squared x minus 1. Since 1 minus 1 is 0, we are left with 2 sine x cosine x minus 2 sine squared x. We can factorize the 2 sine x terms such that we are left with 2 sine x brackets cosine x minus sine x, which matches what the question wanted us to show. For part B, we need to use the information in part A. Since part of the equation in part B has the exact equation from part A, we can replace that part with our answer from part A, which results in the equation 2 sine x brackets cosine x minus sine x plus brackets cosine x minus sine x equals to 0. Since cosine x minus sine x appears in both terms, factorization can be done such that we end up with cosine x minus sine x and 2 sine x plus 1 equal to 0. We can now solve both of these separately to determine all the possible values of x within the provided domain such that the equation holds true. Basically, we need to find all values of x such that sine x equals to cosine x and sine x equals to negative 1 over 2. To do this, you need to make sure to memorize the following unit circle as this is not provided to you in the exam. Recall the left values are all the cosine x values, and the right values are all the sine x values in a unit circle. Using the unit circle, we determine that x can be pi over 4, 5 pi over 4, 7 pi over 6, and 11 pi over 6. Question 6 continues with using trigonometric identities, this time more complicated ones. We are given that cosec theta equals to 3 over 2 over the domain pi over 2 and 3 pi over 2, and we have to compute the exact value of cotangent theta. Recall that cosecant theta is the equivalent of 1 over sine theta, and since its value is positive, it suggests that sine theta's value is also positive. As the domain only covers pi over 2 and 3 pi over 2, Sign values are only positive in the second quadrant, which means our focus should be on the second quadrant only. In the second quadrant, the sine values are positive, but the cosine values are negative. This is important as recall cotangent is equal to 1 over tan theta, and sine over cos is equal to tan, which basically means cotan theta equals to cos theta over sine theta. As we already have determined that sine theta is positive and we are focusing on the second quadrant, all cos values in this quadrant are negative, which means the resulting cotan value that we determine will have to be negative. Now, we can begin solving this problem. Using the Pythagorean identity provided in your formula booklet that 1 plus cotan squared theta equals to cosec squared theta, we can rearrange the identity by making cotan the subject and get the alternative but equivalent identity that cotan theta equals to the square root of cosecant squared theta minus 1. We can substitute cosecant squared theta for 3 over 2, as that is provided in the question, which means we have square root 3 over 2 squared minus 1. We then do 3 over 2 squared, which is 9 over 4, subtract it from 1, which results in 5 over 4. Lastly, we square root 5 over 4. Remember, square root can include both positive and negative values, so simplifying this square root will be plus or minus square root 5 over 2. However, we have already determined earlier that cotan theta's value has to be negative, so we can reject the positive solution and come to the conclusion that the exact value of cotangent theta is negative square root 5 over 2. Question 7 deals with complex numbers. We have a quartic equation z to the power of 4 plus 4z cubed plus 8z squared plus 80z plus 400 equal to 0, where z is a complex number. We are given two roots of this equation, which are a plus bi and b plus ai, where a and b are national numbers, and we have to find the possible values of a. The key to solving this question is using the sum of roots and product of roots formulas. In this case, we have an equation in the form of ax to the power of 4 plus bx cubed plus cx squared plus dx plus a, so the sum of the roots will be minus b over a, and the product of the roots will be e over a. Since the question states that a and b are national numbers, if a plus bi and b plus ai are possible roots, then a minus bi and b minus ai have to be the other two roots for this equation to hold true. Therefore, we can set up our sum and product of roots formulas as such. The sum of the roots are a plus bi, plus b plus ai, plus a minus bi, plus b minus ai, which simplifies to 2a plus 2b. From the formula, we know that this will have to equal negative 4, since our original equation's coefficient for b is 4, and a's coefficient is 1. So we have our sum of roots set up as 2a plus 2b equals to negative 4, which can be further simplified into a plus b equals to negative 2 by dividing both sides by 2. Let's denote this as equation 1. For the product of roots, we have the equation set as a plus bi times b plus ai times a minus bi times b minus ai, and equal that to 400, as e is 400 in our original equation and a is 1. Expanding the brackets of the roots and simplifying it results in a squared plus b squared whole squared equaling 400. We can square root both sides and get a squared plus b squared equals to 20. Let's denote this as equation 2. From equation 1, we can make b the subject such that equation 1 now is b equals to negative 2 minus a. We can substitute this into equation 2, such that we have a squared plus negative 2 minus a whole squared equals to 20. Expanding the brackets, we get a squared plus 4a plus a squared, which simplifies to 2a squared plus 4a plus 4 equals to 20. Dividing both sides by 2 further simplifies this to a squared plus 2a plus 2 equals to 10. We can then subtract 10 on both sides and either factorize or use the quadratic formula to determine the possible values of a. For this video, we will go ahead with the factorization method. After subtracting 10 on both sides, we have a squared plus 2a minus 8 equals to 0. This can be factorized as a plus 4 and a minus 2 equals to 0, thus leading to the answer that a can be negative 4 or a can be 2. Let's move to question 8. This question is a calculus-related question and asks us to use L'Hopital's rule to determine the value of arctan 2x over tan 3x as x approaches 0. In case you have forgotten, L'Hopital's is a calculus method for evaluating limits of indeterminate forms like 0 over 0 or infinity over infinity by taking the derivatives of the numerator and denominator and simplifying the limit problem. It states that if the limit as x approaches for the division of two functions, f of x and g of x results in an indeterminate form, then performing the same calculation but with the first derivatives of both functions can be done to find the appropriate limits to the original functions. So, all we have to do for this question is find the first derivatives of arctan 2x and tan 3x, and then find out the value of the entire fraction as x approaches 0. Firstly, let's set up our functions. Let's make f of x equal arctan 2x, and g of x equal tan 3x. To find the first derivatives of both functions, we will need to make use of the chain rule, as well as refer to the formula booklet that provides the first derivatives of arctan x and tan x. Let's solve the first derivative of f of x first. We can use the chain rule by letting u equal to 2x, such that we have f of u equal to arctan u. Referring to the formula booklet, we know the first derivative of arctan u is 1 over 1 plus u squared. The first derivative of our u dummy variable is 2 since the first derivative of 2x is just 2. As such, the first derivative of arctan 2x is 1 over 1 plus 2x whole squared multiplied by 2, which we can expand and simplify to 2 over 1 plus 4x squared. Now, moving on to solving the first derivative of g of x. Using chain rule again, we let u equal 3x, such that we have g of u equal to tan u. From the formula booklet, we know the first derivative of tan u is secant squared u, and the first derivative of our u dummy variable is 3 since the first derivative of 3x is 3. So, we have the first derivative of g of x set as 3 secant squared 3x. We can now combine both of these together, resulting in trying to find the limit as x approaches 0 of the fraction 2 over 1 plus 4x squared divided by 3 secant squared 3x. Recall that sec theta equals to 1 over cos theta, so we can rewrite the first derivative of g of x such that the limit we are trying to resolve is now 2 over 1 plus 4x squared divided by 3 over cos squared 3x. Simplifying this fraction requires us to multiply the numerator with the reciprocal of the denominator, meaning we have 2 over 1 plus 4x squared times cos squared 3x over 3, which results in our fraction now being 2 cos squared 3x over 3 times 1 plus 4x squared. Substituting x equals to 0 in the numerator and denominator values will result in the fraction 2 over 3, as cos 0 is equal to 1, meaning the numerator ends up being 2 times 1, which is equal to 2, and 3 times 1 plus 4 times 0 squared ends up being 3, resulting in a final answer of 2 over 3. We have come to the last question of Section A. This question deals with permutations and combinations and is arguably the hardest question in Section A for this paper. So, we have a farmer that has 6 sheep pens, arranged in a grid with 3 rows and 2 columns as shown in the following diagram. 5 sheep need to be placed in these pens, and we know that each pen is large enough to hold all the sheep, and that 2 of the sheep in particular, Amber and Brownie, are known to fight. For part A, we need to find out the total number of ways of placing the sheep with the restriction that Amber and Brownie cannot be placed in the same pen. So for this, one way to solve it is to first find out all the possible ways to arrange the sheep in the pens, and then find out how many ways can you include Amber and Brownie in the same pen, and simply take the difference of these values to find out the number of ways in which Amber and Brownie are not in the same pen. To find out the total number of ways to arrange the sheep, we know that each sheep can go into any of the 6 pens independently, and we have 5 sheep to assign in total. So if we take sheep A for example, there are 6 possible pens Amber can be assigned to. Similarly, for sheep B, there are also 6 possible pens that Brownie can be assigned to, as we have to remember that each pen is large enough to hold all 5 sheep. Continuing this for sheep C, D, and E, we determine that there is 6 possible options for each sheep, and since these choices are independent because one pen can have multiple sheep, the total number of ways to arrange the sheep is 6 to the power of 5. Now, we need to find out the total number of ways in which Amber and Brownie are in the same pen. If we assign them into one pen, there are 6 possible pens both of them can be assigned to. As for the other 3 sheep, they are still independent, so the total number of ways for those 3 sheep to be assigned would be 6 times 6 times 6. As we are considering A and B as one unit, given they are to be assigned to the same pen, we would need to multiply the 6 possible options with A and B with the 3 other sheep, meaning we have 6 times 6 to the power of 3, yielding 6 to the power of 4, which represents the total number of ways to assign the sheep with the restriction that Amber and Brownie are in the same pen. Finally, we need to subtract 6 to the power of 5 by 6 to the power of 4 to find the answer to the question, which is to determine the number of ways to assign the sheep given Amber and Brownie are not in the same pen. By subtracting all possible scenarios in which Amber and Brownie are in the same pen, we are able to find the correct answer. Since this paper is a non-calculator paper, you can leave your answer like this and you would get full marks. If you would like to solve it by hand, you can do something like this. We have 6 to the power of 5 minus 6 to the power of 4. We can factorize 6 to the power of 4, such that we have 6 to the power of 4 times 6 minus 1, which simplifies the question to 6 to the power of 4 times 5. You should probably remember that 6 to the power of 4 is 1296, and then we can just multiply it by 5 by hand. 6 times 5 is 30, so we put 0, and carry the 3 to 5 times 9, which is 45 plus 3, which is 48, so we put 8 down next and carry 4 to 5 times 2, which is 10 plus 4, which is 14, so we put 4 down next and carry the 1 to 5 times 1, which is 5 plus 1, which is 6, and put 6 down as the final digit. As a result, the final answer to Part A is 6,480. Part B is quite complicated to solve, so make sure you pay special attention to what is going on so you understand how to solve it. Part B now contains the restriction that each pen can only have at most one sheep, and that Amber and Brownie cannot be placed in a pen where they share a boundary. For example, if Amber is placed in any of the pens, Brownie cannot be placed in any of the adjacent pens, and vice versa. So let's understand our situation. We have 6 pens in a 3 by 2 grid. Let's label it. Row 1 has pens A and B, row 2 has pens C and D, and row 3 has pens E and F. We need to place 5 distinct sheep into each of the pens, meaning there will be one empty pen, ensuring that Amber and Brownie do not share a boundary with each other. Similarly to how we solve Part A, we can determine the total number of ways to assign the sheep without the restriction that Amber and Brownie cannot share a boundary, and subtract that with all the possible scenarios in which Amber and Brownie do share a boundary. This will determine the total number of ways to assign the sheep such that each pen contains at most one sheep, and that Amber and Brownie do not share a boundary. To determine the total number of ways to assign the sheep, we need to first choose one pen to be empty, for which we can choose amongst 6 different pens. After that, we need to assign the 5 sheep into each of the remaining 5 pens available, which means there are in total 5 factorial ways to arrange that. As we can choose amongst 6 different pens to be empty, we have to multiply the 5 factorial ways to assign the sheep with this 6, meaning the total number of ways to assign the sheep is 6 times 5 factorial, which is 6 times 120, resulting in 720 ways to assign the sheep. Now, we calculate the total number of ways in which Amber and Brownie do share a boundary. We need to determine out of the 720 ways to assign the sheep, how many arrangements have Amber and Brownie in adjacent pens, and subtract these scenarios from 720. We can draw up the 6 pens and mark their neighbors like this. For pen A, which refers to row 1, column 1, its neighboring pens are pen B, which is on the right, and pen C, which is below. This is repeated for the other 5 pens. We fix which pen is empty, and then look at the remaining pens and see which original adjacent pairs are still present in these 5 pens. If we think about it logically, for each such pair, if we put Amber in one and Brownie in another, that would be a bad arrangement for that empty pen choice. We know that this will be symmetrical, meaning the total number of ways to assign Amber and Brownie next to each other would be the same for each corner pen and the 2 middle pens. As such, what we can do is find out the total number of scenarios that Amber and Brownie are in an adjacent pen given one of the corners is selected as the empty pen, multiply that by 4, and then find out the number of scenarios they are adjacent given one of the middle pens are empty and multiply that by 2, and then add both values together to determine the total number of scenarios that Amber and Brownie share a boundary. So let's assume pen A is marked as the empty pen, meaning pens B to F are non-empty. The original adjacent pairs that still exist are pens C and D, pens E and F, pens C and E, pens D and F, and pens B and D. Those are 5 adjacent pairs of pens in total. For each such pair, there are 2 ways to assign Amber and Brownie, as we can put Amber in the first pen and Brownie in the second, and vice versa, and then we have 3 factorial ways to assign the remaining 3 sheep to the 3 available pens. As such, the total number of ways to assign the sheep where Amber and Brownie share a boundary and given pen A is taken as the empty pen is 2 times 5 times 3 factorial, which results in 60. Now, since there are 4 corners, and we know this is going to be the same case if we take pen B, pen E, or pen F as the empty pen, we can multiply 60 by 4 to cover all the corner pen scenarios. This means so far we have 240 arrangements in which Amber and Brownie share a boundary. We now need to shift our focus to the middle pens. Let's take pen C as the empty pen now and repeat the process. From the original list of adjacent pens, we have pens A and B, pens B and D, pens D and F, and pens E and F, meaning a total of 4 adjacent pairs. Each pair will have 2 ways to assign Amber and Brownie, and 3 factorial ways to assign the remaining sheep. So, the total number of ways to assign the sheep given Amber and Brownie share a boundary if we assume pen C is the empty pen is 2 times 4 times 3 factorial, which is 48. Since there are 2 middle pens, the same will be true if we assume pen D is empty, so we can multiply 48 by 2 and determine that the total number of scenarios that Amber and Brownie share a boundary given that one of the middle pens are empty is 96. Adding 240 with 96 results in a total of 336 arrangements where Amber and Brownie share a boundary. Therefore, the answer to the question is simply 720 minus 336, which is 384, meaning there are a total of 384 ways to assign the sheep to the pen such that each pen contains 1 sheep and that Amber and Brownie do not share a boundary. Let's begin with section B of this paper now. Question 10 is a statistics and probability question about biased dices. We are given a 4-sided biased die with the following probability distribution in terms of P. For part A, we simply need to determine what this value of P should be. Remember, if you are given a probability distribution table, all the values in that table have to be between 0 and 1, and the sum of all the probabilities should be 1, since you cannot have a probability be less than 0 or greater than 1. So, we can sum up all the different probabilities mentioned in the table, equal it to 1, and solve for P. We have P plus P plus P plus 1 over 2P, which when we add up simplifies to 7 over 2P. We set this equal to 1, and by making P the subject, we can determine that P equals 2 over 7. Part B asks us to determine the expected value of the probability distribution table. From the formula booklet, we know to find the expected value of a discrete random variable. We can multiply each of the possible values with their respective probabilities and sum them all up. So that is what we need to do. We have 1 times P, plus 2 times P, plus 3 times P, plus 4 times 1 over 2P. Adding these up results in an expected value of 8P, which when we substitute our answer from part A, we get the expected value of 16 over 7. Part C has given us another biased die, B, with a different probability distribution table with probabilities represented in terms of Q and R. For the first part of Part C, we have to provide the range of possible values that it can take in this distribution. Recall that any probability in a probability distribution can be between 0 and 1, so therefore R can be between 0 and 1. For the second part of Part C, we have to determine the range of values of Q. To do this, we can take the extreme ends of possible values for what we just identified, and use them to solve for Q, as remember all probabilities in a distribution table must add to 1. So if we assume R is 0, then the probability distribution will have 3Q equaling 1, which when we divide 3 on both sides, we get Q equaling 1 over 3. Similarly, if we assume R is 1, then that naturally implies that Q has to be 0, since the probability distribution already adds up to 1. Therefore, the range of possible values for Q are between 0 and 1 over 3. Part D asks to find the expected value of Y. Similarly to how we computed the expected value of X in Part B, we can multiply all the possible values with their respective probabilities in the table, so we get 1 times Q, plus 2 times q, plus 3 times q, plus 4 times r, which simplifies to 6q plus 4r. Now, to determine the range of possible values for the expected value of y, we know from part C that when r is 0, q is 1 over 3, and when r is 1, q is 0. We can substitute these limit pairs into our expected value of y that we have, to determine the range for the possible expected values of y. So, if we assume r is 0, then q is 1 over 3, which means the expected value of y will be 6 times 1 over 3 plus 4 times 0, which results in 2. Repeating this for when r is 1 and q is 0 yields an expected value of y of 4. Therefore, the range of possible values for the expected value of y is between 2 and 4. The final part of question 10 presents us with a scenario in which we have two players, Agnes and Barbara, who play a game using these dice. Agnes rolls die A once and Barbara rolls die B once, and we are given that the probability that Agnes's score is less than Barbara's score is 1 over 2. Based on this information, we have to calculate the expected value of y. Okay, so the first step is to understand the probability distributions we have for both players. Agnes's probability distribution table looks like this, and Barbara's probability distribution table looks like this. Although we know that the probability that Agnes's score is less than Barbara is 1 over 2, we can use this information to determine the expected value of y. We can compute the probability that Agnes's score is less than Barbara as the probability of Agnes's score multiplied with the probability that Barbara's score is larger than Agnes's, and sum up all the possible scenarios this can occur. Note we only sum up to 3 because if Agnes rolls a 4, then it is impossible for Barbara to roll a higher number, and since we are only interested in the cases in which Agnes's score is less than Barbara's, we do not include the scenario in which Agnes rolls a 4. Let's determine the probabilities that Barbara's score is larger than Agnes. If Agnes rolls a 1, then the probability that Barbara's score is higher is if she rolls a 2, 3, or a 4. So according to Barbara's distribution table, the probability of her rolling a 2, 3, or a 4 is q, q, and r respectively. Summing this up and representing r in terms of q results in a probability for this scenario to be 1 minus q. Now, what about if Agnes rolls a 2? Then the probability that Barbara's score is higher is if she rolls a 3 or 4. So according to Barbara's distribution table, the probability of her rolling a 3 or a 4 is q, and r respectively. Summing this up results in a probability for this scenario to be 1 minus 2q. Lastly, if Agnes rolls a 3, then the probability that Barbara's score is higher is if she rolls a 4. So according to Barbara's distribution table, the probability of her rolling a 4 is r, meaning the probability for this scenario is 1 minus 3q. So putting everything together, we have to multiply the probability that Agnes rolls a 1 with the probability that Barbara will score higher, add it with the probability that Agnes rolls a 2 with the probability that Barbara will score higher, and add that with the probability that Agnes rolls a 3 with the probability that Barbara will score higher. This will be 2 over 7 times 1 minus q, plus 2 over 7 times 1 minus 2q, plus 2 over 7 times 1 minus 3q. Factorizing the 2 over 7 out, and simplifying the brackets results in 2 over 7 times 3 minus 6q, which when we expand the brackets yields 6 minus 12q over 7. Now we can use the information provided in the question that the probability that Agnes's score is less than Barbara is 1 over 2 by setting 6 minus 12q over 7 equal to 1 over 2, and solve for q. We can cross-multiply such that we have 12 minus 24q equal to 7, and then subtract 12 on both sides to get negative 24q equaling negative 5. Since there are negatives on both sides of the equation, they cancel each other out, and we can finally divide 24 on both sides to get us a value of q equaling 5 over 24. Great, hard part's done. Now we just need to substitute this value of q back into the probability distribution table shown in the question for die B, and compute the expected value of y. The probability distribution now has probabilities 5 over 24 for scores 1, 2, and 3 over 8 for a score of 4. So computing the expected value of y by doing 1 times 5 over 24, plus 2 times 5 over 24, plus 3 times 5 over 24, plus 4 times 3 over 8, results in an expected value of y of 11 over 4 after simplification. Question 11 deals with vector planes and Cartesian equations. We are given a line with a Cartesian equation, and for part A, we need to show that a specific point lies on this line, and then find a vector equation for the line using the Cartesian equation provided. For the first part of part A, all we need to do is substitute the x, y, and z values into the Cartesian equation, and if they all yield the same value, then it means this point lies on L1. So we substitute x for -1, y for 0, and z for 3, and notice they all equal to 0, meaning the point -1, 0, 3 does in fact lie on L1. For the second part of part A, we can set up a vector equation using lambda, and set each of the three equations equal to lambda, and make x, y, and z the subject for each of the equations. So for x, we have x plus 1 over 2 equaling lambda, and if we make x the subject, we end up with x equaling 2 lambda minus 1. For y, since y equals lambda, nothing needs to be done, and for z, we have 3 minus z equaling to lambda. Making z the subject results in z equaling 3 minus lambda. Now that we have our three equations, we can separate the constants and the lambda values, such that we take the coefficients of the lambdas. So the constants for the x, y, and z equations are -1, 0, and 3 respectively, and the lambda coefficients for the equations are 2, 1, and -1 respectively. Therefore, we can set up the vector equation as -1, 0, 3, plus lambda, 2, 1, -1. We are given a second line with a vector equation, r, and are asked to find the possible values of when the acute angle between the two lines is 45 degrees. We can make use of the following formulas in the formula booklet. Remember, we only deal with the coefficients when doing the dot product of two lines, so we will assign v to L1 and w to L2, and set up the equation as 2, 1, -1, dot, hey, 1, -1, equals to the magnitude of 2, 1, -1, multiplied by the magnitude of hey, 1, -1, multiplied by cos 45. Using the formula in the formula booklet to carry out the dot product, we have 2 times hey, plus 1 times 1, plus -1 times -1, which we set equal to the square root of 2 squared plus 1 squared plus -1 squared, multiplied by hey squared plus 1 squared plus -1 squared multiplied by square root 2 over 2. Since you should know if you have memorized the unit circle that cosine 45 is square root 2 over 2. Simplifying the left-hand side of the equation results in 2a plus 2 equaling square root 6 times square root hey squared plus 2 times square root 2 over 2. We can multiply the square root 6 and square root 2 together to get square root 12 times square root hey squared plus 2 over 2. We can simplify square root 12 as 2 square root 3, such that we can get rid of the 2 in the denominator. We end up with 2a plus 2 equals square root 3 hey squared plus 6. Now, to solve for hey, we can square both sides of the equation such that we are not dealing with square roots anymore. Expanding 2a plus 2 squared yields 4a squared plus 8a plus 4, and the right-hand side of the equation becomes 3a squared plus 6. Moving all the terms to one side and setting the equation to 0 will allow us to use the quadratic formula to determine the possible values of hey. So, we have hey squared plus 8a minus 2 equals to 0. And now using the quadratic formula will yield the possible values of hey being -4, plus or minus 3 square root 2. Moving on to the last question of this paper, we have a calculus question. We are given a function f of x, which is equal to the square root of 1 plus x for x greater than -1. For part A, we are asked to find the second derivative of f of x. In order to do this, let's first find the first derivative of f of x. Using chain rule, which is provided in your formula booklet, we can set u equal to 1 plus x, from which we have f of u equals to the square root of u. Recall that the square root of a variable is the same as saying that variable is raised to the power of 0.5, or 1 over 2. So, we can represent f of u as u to the power of 1 over 2. So the first derivative of u to the power of 1 over 2 will be 1 over 2 square root u. Remember, we need to differentiate our u dummy variable as well, which in this case is just 1 since the first derivative of 1 plus x is just simply 1. So, substituting x back into the equation, we find out that the first derivative of f of x is 1 over 2 square root 1 plus x. To find the second derivative of f of x, we need to repeat this process, but now we use the first derivative of f of x as the function that we will be differentiating. So, using chain rule again, we let u equal to 1 plus x, and have the first derivative of f of u equal to 1 over 2 times u to the power of negative 1 over 2. Remember, if you bring a positive exponent from the denominator to the numerator, or vice versa, the exponent becomes negative. So now we differentiate this again, and we have the second derivative of f of u is negative 1 over 2 times 1 over 2 times u to the power of negative 1 over 2 minus 1. Simplifying this yields negative 1 over 4 times u to the power of negative 3 over 2. Let's not forget to differentiate our dummy variable u, which is still 1 as the first derivative of 1 plus x is 1. Recall that a variable raised to the power of 3 over 2 is equivalent as saying the square root of that variable, cubed. So, after substituting x back into the equation, we come to the final conclusion that the second derivative of f of x is indeed negative 1 over 4 square root 1 plus x whole cubed. Part B is about using mathematical induction to prove that the given formula holds true for all cases given that n is larger than 2. To start off, we test out if the formula holds true when n equals to 2. Substituting n equals 2 into the formula yields the second derivative of f of x to be negative 1 over 4 square root 1 plus x whole cubed, which we know is correct based on our calculation in Part A. Therefore, we can conclude the formula holds true for n equals to 2. Next, we assume a dummy variable, say k, holds true and set n equal to k and rewrite the formula using k instead of n. If this is the case, we can consider the case that n equals to k plus 1, and evaluate the left-hand side and right-hand side of the formula separately. If they indeed equal each other, then we are able to prove by the principle of mathematical induction that the formula holds true for all cases given that n is larger than 2. So if we evaluate the left-hand side of the equation, we have to find the k plus 1 derivative of f of x, which is basically the same thing as differentiating the kth derivative of f of x one extra time. This means we can represent the left-hand side of the formula as differentiating the kth derivative of f of x with respect to x. We know from when we let n equals k what the kth derivative of f of x is, so we can use that to differentiate it one extra time. Notice that since we are differentiating with respect to x, the only thing that needs to be differentiated is the 1 plus x to the power of 1 over 2 minus k, as the rest of the terms are all a constant coefficient. So, employing chain rule like we have done, we can determine that the derivative of the k plus 1 derivative of f of x is negative 1 over 4 to the power of k minus 1 times 2k minus 3 factorial over k minus 2 factorial times 1 over 2 minus k times 1 plus x to the power of minus k plus 1 over 2. Now that we have the left side of the formula set up, we are going to play around with the right-hand side of the formulas such that we can end up getting this, which we have denoted as equation 1 over here. If we look at the right-hand side of the formula, substituting n equals to k plus 1 starts us off with this. Let's do some basic simplification first by doing k plus 1 minus 1, expanding the brackets and the factorials and simplifying them, and simplifying 1 over 2 minus k plus 1. Doing these simplifications results in having negative 1 over 4 to the power of k times 2k minus 1 factorial over k minus 1 factorial times 1 plus x to the power of minus k plus 1 over 2. This is where you might feel stuck now on how to progress. Well, one interesting observation to note is that the left-hand side of the formula has negative 1 over 4 raised to the power of k minus 1, whereas here on the right-hand side, we have it raised to the power of k. So what we can do is rewrite negative 1 over 4 to the power of k as negative 1 over 4 to the power of k minus 1 times negative 1 over 4, as this equals negative 1 over 4 to the power of k. At the same time, we can begin expanding the factorial to see if we can cancel out any like terms in the numerator and denominator. Doing this, we stumble upon 2k minus 2, which if we factorize by taking the 2 out, results in 2 times k minus 1. Since k-1 is also in the denominator, we are able to cancel one of the terms out. So, employing these changes results in us having -1/4 to the power of k-1 times -1/4 times 2k-1 times 2k-2 times 2k-3 factorial over k-1 times k-2 factorial times 1 plus x to the power of -k plus 1/2. We can cancel the k-1 terms in the numerator and denominator, and simplify the 2 on the numerator with the 4 on the denominator, which leaves us with -1/4 to the power of k-1 times -1/2 times 2k-1 times 2k-3 factorial over k-2 factorial times 1 plus x to the power of -k plus 1/2. Simplifying the -1/2 times 2k-1 term leaves us with the result -1/4 to the power of k-1 times 2k-3 factorial over k-2 factorial times 1/2 minus k times 1 plus x to the power of -k plus 1/2. This matches the left-hand side of the equation, meaning it matches equation 1. Therefore, we can conclude that this formula is also true for n equals to k plus 1. Finally, we need to write a conclusion to summarize our findings. We can conclude that if n equals to 2 is true, and we assume that n equals to k is true, then it must be true that n also equals to k plus 1. Hence, by the principle of mathematical induction, the nth derivative of f of x holds true for all n larger than or equal to 2. For the final part of this question, we are given a new function, h of x, which is a function that uses both f of x, which is square root 1 plus x, and g of x, which is e to the power of m times x. We are given that the coefficient of the x squared term in the Maclaurin series of this function is 7/4, and based on this we need to find the possible values of m. The Maclaurin series formula is provided in your formula booklet, and we can see that the x squared term is associated with the second derivative of a function in the series. As such, we need to compute the second derivative of h of x first. Let's do that. We have h of x equal to a to the power of m times x times the square root of 1 plus x. We can use product rule, which is provided in your formula booklet, to solve the first derivative of h of x. We let u equal to the square root of 1 plus x, and v equal to a to the power of m times x. Deploying product rule, we differentiate v first, which is m times e to the power of m times x. As recall, we're using chain rule here, and the first derivative of m times x is m, and the first derivative of e to the power of x is e to the power of x. We then differentiate u, which we have done previously in part a, so we know it is 1/2 times the square root of 1 plus x. Factorizing the like term of e to the power of m times x, we have the first derivative of h of x as e to the power of m times x, times m times the square root of 1 plus x, plus 1/2 times the square root of 1 plus x. We now proceed with using the first derivative to find the second derivative of h of x by repeating the process. We let u equal a to the power of m times x, and v equal to m times the square root of 1 plus x plus 1/2 times the square root of 1 plus x. Differentiating v first, we get m/2 times the square root of 1 plus x minus 1/4 times the square root of 1 plus x whole cubed. Differentiating u gets us m times a to the power of m times x. This means the second derivative of h of x is e to the power of m times x times m/2 times the square root of 1 plus x minus 1/4 times the square root of 1 plus x whole cubed plus m times the square root of 1 plus x plus 1/2 times the square root of 1 plus x times m times e to the power of m times x. Substituting x equals 0. We have m/2 minus 1/4 plus m plus 1/2 times m, which after further simplification yields m squared plus m minus 1/4. Now, we make use of the Maclaurin series coefficient that the x squared term's coefficient is 7/4. As the coefficient is represented as x squared over 2 factorial, we have to multiply 7/4 by 2 factorial to get the actual coefficient, which is 7/2. We can then set 7/2 equal to m squared plus m minus 1/4, and solve for m. We can multiply 4 on both sides such that we have 14 equals to 4m squared plus 4m minus 1, then subtract 14 on both sides, such that we have 4m squared plus 4m minus 15 equals to 0. We can use factorization or the quadratic formula to solve this question. For the purposes of this video, we will use factorization. Factorizing this equation results in getting 2m plus 5 times 2m minus 3 equaling 0. Therefore, we can conclude that if 2m plus 5 equals to 0, then m equals to negative 5 over 2, and if 2m minus 3 equals to 0, then m equals to 3 over 2. Hence, the possible values of m are negative 5 over 2 and 3 over 2. We have finally completed the exam paper. Hope you enjoyed the video and hope you learned something. See you next time.